Okay, so hello everyone, welcome back. I'm delighted to introduce Omri Weinstein. Omri was a Mark's PhD student at Princeton, and then he did a postdoc at NYU, had a position at Columbia, and is now at the Hebrew University. And Omri has done some very exciting work in data structures, in information theory, communication complexity, and today he'll talk to us about perhaps a different topic. I'm not sure. We'll find out.
Slightly different. Yeah.
Yes.
Thanks, everyone. Thanks for sticking to the talk. I can't help us start with a brief story about Mark. So I was lucky enough, as most of you know, to be Mark's first student and in Princeton. And the typical way our meetings would go is that I would just knock on his office, get inside and see Mark often, lying on his bright orange Princeton couch. And I would start, to fill in the board and just blather about all sorts of ideas. I would squint and see Mark seemingly taking a nap, and I would just keep blathering and, filling on the board. And Mark would still just, complete silence. And then after like 45 minutes, he would just wake up and say, okay, we need to go, so let's just solve it. And would literally walk up to the board and write the solution to the problem. And that happened multiple times. So this was like problems which we've been thinking about for weeks or for whatever. So apparently he was not asleep, but you can imagine my disappointment that this was the standard I got used to. So leaving Princeton was not. I remember myself surprised that this is not the usual interaction with any researcher. And as we all know, Mark, a lot of Mark's work was in the intersection or union of information, computation, and economics. And even though Mark was not on this specific work, a lot of this work was inspired by this intersection, Mark's philosophy, and in particular by this philosophical question that Mark kept asking me since the day we met, whether we can define some invariant measure of unit for real computation analogous to bits of information, which I must admit I've never really digested this. And I'm not saying this is what we're going to see today, but yeah.
Does the word real in that question refer to like
the real numbers? Yeah.
Right.
You can ask Mark, but yeah. And so I guess I'm not claiming that this is what we'll see here, but a lot of this work was inspired by this question. And what I'll talk about is this new cryptographic primitive, which intertwines computation, information or data, and money into a single atomic operation, which happens to be a new way to multiply matrices. And this operation is really atomic. You can't split it in any way. I hope this will become clear. And as it turns out, this does seem to create some measure of turning general compute into or real-world computation into some fungible currency. So some measure of tokenization of general compute. And I hope this will become clear throughout the talk. So Bobby said that he feels dirty for showing a picture of DeepMind in a maths institute. They should probably kick me out now. But so the backstory here, or the background is really the Bitcoin or blockchains. And I won't assume much about this, but I presume that most of you vaguely know. So how many people here vaguely know how Bitcoin works or how blockchains work? Cool. All right, so the goal in blockchains is to basically the original goal was to implement a bank without a central authority, right? A permissionless system. But in essence, blockchains are just a distributed data structure, all right, where there's no shared blackboard, there's no shared state, and the goal is to implement this asynchronous permissionless data structure. By permissionless, I mean that there is no onboarding process. The number of users that participate can change dynamically, and there's no authentication process for onboarding or deporting users. And by asynchronous, I mean that everything happens, like there is no a priori bound on the delay of broadcasting messages. So each one has his own computer, and we broadcast messages, and we hope that after some finite, hopefully short amount of time, if we behave honestly, then the transaction will be accepted by the chain. And of course, the main question here, without diving into the detail, is how do we even agree on the update on the state of this data structure, right? How do we collectively update a distributed data structure where there is no central authority, right? So each one of us has her own local view, and there is no coordination system here, right? And that by itself that's the problem that Bitcoin essentially solved, and that by itself was conjectured impossible. So that was not even clear how you can do that. And to build intuition of how you would try to do that, so kind of the first idea that comes to mind is to just cast a majority vote, right? If there's no honest majority in any distributed system, there's nothing you can hope for, right? So let's assume there's an honest majority, in which case the most natural idea is to cast a majority vote. But of course, a majority vote it's not permissionless, right? You need to solicit, votes from each player. And in fact, forget the computational issues or feasibility. Majority votes or soliciting votes is actually not secure, because people may abstain from reporting their vote. And actually that leads to very nasty collusion strategies, which simply bias the results arbitrarily. So that's actually not secure. And then the next idea is, by the way, this was the result by Pasanchi. That was kind of the impossibility result that I was referring to. And then the next idea is to actually do a random lottery, right? To just kind of pick sample a random leader and let her decide whether to accept the next update to the data structure or not. Does that make sense? But then the question, of course, is, who draws the randoms? Again, remember, there's no blackboard, there's no central authority. Each one of us has her own local views, right? So it's not clear who draws the randomness. It's not even clear what's the support of this distribution, right? Because the number of users or the number of computers is not fixed, right? And I think really, if you want to take one key idea from Bitcoin, this is what Bitcoin really solves. It designates who's allowed to vote in this system. And what Bitcoin says is that the person that's allowed to vote voting entails a demonstration of an expensive but abundant resource, right? So it cannot be cheap to vote, okay? And in fact, if voting is cheap, if it's for free, this is exactly why distributed consensus was conjecture impossible, because I can just pretend to be 1 million voters, and then I'll talk to Shibangi. Shibangi will believe that I'm just 1 million voters, and I'll lead her. I'll easily be able to fool her to accept whatever decision. But if voting, if Sybil attacks or pretending to be 1,000 voters is actually expensive, this kills this attack. Does that make sense? All right. So, questions?
You haven't said that fairness is one of the objectives or constraints on the design here.
Fairness in what sense?
I don't know. But rather than sampling a leader at random.
Oh, I see. Okay.
What about just appointing Elon Musk to be the leader?
I see. So I guess that would require authentication in some way. But I guess the whole story here is that this is how Satoshi's original paper is cast, is the idea is to simulate a majority vote. So if you could actually have a finger stamp for each voter, that would be ideal. Unfortunately, that won't be permissionless, so that you cannot do this. So the best approximation was this proof of work idea, which we're going to get to in a second. So if I didn't answer the question, I'll come back to it later. But the guiding, and this was actually the guiding principle beyond all of the consensus mechanisms that emerged after Bitcoin, which is that users or miners or whatever will invest expensive but abundant resources. It can be space, capital, communication, electricity, whatever. And this will secure the system in a way that we'll explain in a bit. And in exchange, they will receive rewards, incentives to invest those resources. All right. And okay, I just want to say one more thing that, oh, sorry. Yeah, so, and that, this concept kind of mimics scarcity in hard assets, right? So, okay, I'll just say it. So, if you ask yourself, why is gold more expensive than plastic? Then the immediate reaction is, well, plastic, gold is more rare than or scarce than plastic. But actually, when you think about it, scarcity is not, it's just a means to an end. The important property of gold is that it's hard to counterfeit gold, right? It's just hard to produce gold. It's much harder to counterfeit than plastic. Bitcoin achieves scarcity or inability to counterfeit through computational hardness, through expenditure of electricity, okay? And this leads to the classical proof of work idea, which actually was invented. So it turns out that electricity or computation has this both properties. It's accessible to everyone, but it's expensive, right? It's not for free. Yeah, we will, okay. I was sure that. Yeah, so yeah, sorry, that was a bad choice of palette here. So the concept of proof of work was invented by Dworkin Orr way before Bitcoin, was actually in a context of deterring spam, like spam filtering, where the idea was that in order to vote, in this case, send a spam, send a message or spamming, entails solving a difficult problem, which in turn requires a lot of energy, computational electricity, and so forth. And Bitcoin is essentially a way to harness this idea in order to achieve distributed consensus in the following way. So in this Nakamoto consensus protocol, we have transactions in the blockchain organized into blocks, right? So each block consists of a block header or a unique ID, right? So some hash ID. And so this is the data structure. It's just a chain of blocks grouped with updates or transactions. Suppose we want to, some user wants to update the data structure. So Alice wants to transfer Bob $50 or 50 coins in exchange for some, bicycle or whatever. And, right? And the way she'll do it is she will try to update or send, the way to add this transaction to the ledger, to the data structure, is through one single update operation called extending a block. And the key, so what is this update operation? Well, extending a block is just a way to basically add another block to the chain as a successor of this current block. And this operation is defined as follows. If Alice wants to add this transaction to the blockchain, and she can work on her favorite block, like this operation is extending a block applies to any block, right? And a block can be extended by a million different operations. Remember, it's a completely free and permissionless chain. Extending a block requires solving this hard puzzle. So Alice will hash the hash ID of the previous block she's trying to extend. She will add the transaction, encode it, and then extending the block to this will require Alice or whoever approves the transaction to find a completing string that will make a random hash function evaluate to some small number. Okay, and this small number is called the proof or the lottery ticket. And this small number today is called the difficulty parameter of the blockchain. Today it's something like 47 trailing zeros, right? So the probability of a random or of any specific guess to this thing, the probability to succeed is something like 2 to the minus 47, right? Does that make sense? So again, that's the only operation allowed in this chain. And now, oh, and that's actually important. So let me just say, and the important thing in Bitcoin is that the difficulty parameter is dynamically adjusted to be roughly a constant, let's say 10 over the total hash power, or the total, think of hash power as just the number of guesses per, that we, number of user, the number of lottery tickets or electricity spent in the system right now, right? So remember, it's a permissionless system, so the hash rate could go up or go down. We don't care about the number of users. All we care about the hash rate, which we can track, right? Because we know from the previous block how much time and expectation it took us to find another block. So we have a very good, unbiased estimator about the hash rate. And Bitcoin dynamically adjusts the difficulty, the number of zeros in, the trailing zeros in the target hash to be threshold to be roughly 10 over the difficulty. What does that mean? It means that no matter how many users or compute cycles are invested in the system now, it can be 1 million users or 10 billion users, the expected time of a winning lottery ticket will be what? If this is the difficulty parameter, 10 over the total hash power, then how long do you expect it to take for some lottery tickets to win this game, to open the block? 10 minutes, right? So really what Bitcoin is really, it's a distributed clock that clicks every 10 minutes, no matter how many users there are. And that's actually the useful way to abstract this, this process. And of course, in this case, so honest behavior, honest miners are defined to be miners that believe only the longest chain. Okay, so what's special about this, the longest chain, right? So honest user will always try to extend the last block. But of course, in this case, Bob, Alice could try to cheat the system by trying to, so she'll add the transaction to the block. She'll get her bicycle from Bob, right? But now she'll try to undo the transaction and receive her 50 coins back. How can Alice do that? What does Alice need to do in order to erase this transaction and, basically game the system? She needs to find a longer chain. So what's the conceivable way to do that? Of course, there are potentially many ways, but she could try to re-extend this block, erase the transaction, and then find, a longer chain which exceeds the length of the longest chain. And in this case, she got her bicycle and she didn't pay for it, right? She just managed to erase her transaction. Right, so does that make sense? So this is one possible attack, which was studied in the original Bitcoin paper. And the main theorem in the original Bitcoin paper is that actually, if you look at the longest chain, which is the random variable, at any time step t, if you look at the longest chain, and then you look k blocks or 6 blocks deep inside the chain. So you look k blocks buried into the longest chain. This block is considered secure in the sense that every block, every transaction that's buried at least 6 blocks deep or k blocks deep will never be erased, or it will be erased with probability exponentially small in K. So that's a security assumption of Bitcoin. And the analysis, I won't show, this is basically an exercise in martingales, but the intuition here is pretty clear that you have these competing chains. If you have an honest majority trying to extend the longest chain, and then you have a minority trying to compete against the chain. So it's a race between, you can view it, you model this as a martingale, but the important thing is that you can completely abstract all the proof of work and all the computation, everything. All you need in order to prove this theorem is to view a blockchain as a Poisson process with, where the arrival time of the next block is just a Poisson process with some parameter. In Bitcoin, it's 10 minutes. That's all you need. So this abstraction allows for the full analysis. And really, my point here is that really if you think of what is proof of work, or what is proof of work consensus, it's really just a distributed clock that clicks every 10 minutes. And that's all the properties of Bitcoin follow essentially from this property. And it ensures, for example, the consistency of the chain and the liveness. Liveness means that, well, if I'm honest, then after a constant number of clicks, my transaction will be digested in the system, right? It doesn't make sense to build a data structure where I have no guarantees when, even if I'm honest, there's no guarantee, about it, when this will be digested. And my point here is to emphasize that, to get this distributed clock that clicks every 10 minutes, you really need the hard problem to be uniformly hard, flat, right, for everyone, right? So the property you need is that any lottery ticket pi, which is the proof of work, that's produced using a p fraction of the total energy or electricity in the system, you really want it to win with probability, with the fair probability, but p with probability p, right? Does that make sense? Because if there's a non-uniform hardness here, right? If there's a way to game the system by investing less than p resources and winning with probability larger than p, then the clock will not click every 10 minutes, right? It will click every, I don't know, like 2 minutes or 2 seconds or whatever. And any monetary system where you can't control the production of new coins goes haywire, right? Does that make sense? Yeah.
So then only if you have approximately p, even if it's tiny different from p, I can start with creating a drift there and then.
So in theory, so by the way, this does happen in practice because Bitcoin is mined using specialized hardware today. So there is some gap, there are some gaps between, you cannot mine Bitcoin with CPUs today, right? Or even GPUs, right? You need special hardware. So there are like differences here, but I think the protocol is robust to this approximation. I'm not sure this is accounted for in the theoretical analysis though.
Theoretically, you don't, what is that approximation?
Here, I don't think it's not a formal claim that I'm making. It's just, okay, let me put it this way. If you're mining 1,000 times faster than I am for whatever reason, then I'll drop out, right? I won't participate, right? So that's what's happening today. And besides of that, if there's if the cost of production for a single player in the system is very, very cheap, then you cannot control really the behavior of this system. You no longer have this Poisson property anymore, right? So my point is that uniform hardness is crucial. And that's what's nice about random hashing, right? It has this property that there is no clever algorithm. There is no way it's uniformly flat for anyone. If I invest 1,000 times more electricity than Mark, then Mark won't envy me, so then, once every 1,000 times, Mark will win the lottery. But he won't be envied because I expended 1,000 times more energy. So this is the right kind of this is the fair probability of win. Does that make sense? All right. So Fast forward 20 years, we know Bitcoin actually works. It's worth a lot of money, but that's, that's not the aspect I'd like to highlight here. It's more about the fact that it's actually, it works, right? So it seems that the system is pretty stable, and it proved that humans can actually, implement this system where trust is not, it's only enforced mathematically, right? There's zero trust in the system. What enforces truthful behavior is math, right? It's just mathematics. And of course, the drawback is that Bitcoin wastes a lot of energy, right? So today I think it's around 1.7 global electricity, more than Switzerland and Norway, just on those random hashes, right? And there's been a lot of alternative suggestions for replacing electricity with other resources like proof of stake, like where you invest capital instead of energy. Let me not go in there. Those protocols are essentially broken. It might take 10 or 20 years to figure this out. But just to give you an idea, Ethereum, which is the second largest blockchain, where the consensus is based on the resource is based on staking money as opposed to real burning energy. There's a single entity owning 30% of this network. And this entropy, so the rich get richer, right? Because the dominant strategy in those networks is to hoard your money, because capital is what makes you more capital. So there's no incentive to sell your tokens. In Bitcoin, it's exactly reversed. The dominant strategy is to sell as much Bitcoins as you have in order to burn electricity in the real world. That's in principle the right thing to do. So this breaks the cycle between the cyclic thing. Like you need to be pegged to some real world resource. That's what it seems. All right. And the Holy Grail was, of course, trying to come up with a useful proof of work where, sure, we'll still peg ourselves to computation, but now, why not exhibit as a proof of work a work that needs to be done anyway, right? That, why not write on top of a work that, it's already being done? And that was, conjecture that was raised in the very first Dwork-Nour paper, where they said, the evaluation of the hash function serves no useful purpose except serving as a deterrent. It would be exciting to come up with a scheme where evaluating the function serves additional purpose. And then 2019, Vitalik Buterin, the founder of Ethereum, reiterated this and said that if we can find some useful proof of work, basically he called it folding at home, to folding proteins or graph search or any DNA sequencing, whatever, then cryptocurrency mining will actually become a huge boon to society, not only removing the objection that Bitcoin wastes energy, but even being societally beneficial. And then he adds in this blog, it's probably infeasible. And like a year later, Ethereum switches from proof of work to proof of stake. So this was as if admitting that useful proof of work seems intractable. And there was a long line of work attempting to do those things. And this is essentially, this is our contribution in this work. How much time do I have? All right, cool. All right, so let's first mathematically define what is a useful proof of work, right? So for any real world task F, think of it as, DNA sequencing, graph search, flow problem, whatever. Like, let's define, suppose that the worst case complexity of this task or this function is T of n, right? So for sorting, it will be n log n. For matrix multiplication, it will be n cubed, or assuming naive matrix multiplication. For, I don't know, maximum flow, it would be, again, there's a difference between theory and practice here, but we'll discuss this in a bit. So what is a proof of useful work protocol for F? Well, it's defined, so the way we define it is the following. It's composed of two functions, solve and verify. So solve receives, as before, as in Bitcoin, the nonce, the identity of the previous block that you're trying to extend, which you can think of as just the ID, the hash ID. But here there's an additional parameter x, which is the input you're trying to solve, right? So this is the useful part. So think of x as some useful task, some DNA sequencing problem that someone is willing to pay you for computing it, right? That's how we define useful work, right? A task is K useful, or someone is willing to pay K dollars for this task to be completed, right? So it's completely external to the system, to the blockchain. Make sense? So now the output of solve should be, instead of Bitcoin, which was just the proof of work, pi, right? Just the missing completing hash string. Now there are two outputs. It's the lottery ticket pi, the proof, and the output, the useful the output y, which should be the f of x, right? The real computation that you need to do regardless of the system. That makes sense? All right, and then the other function is verify, which gets the nonce, the block you're trying to extend. It receives the proof pi, right? Exactly as in Bitcoin's proof of work. But then, and it should satisfy the following constraints, right? So, yeah, ignore this for a second. I'll explain in a second. So, first of all, the time for solve. So, intuitively verify should act exactly like in Bitcoin, right? So, the probability. So, if you produced any lottery ticket, right, in time t of x, which is the worst case time that you're going to spend on solving your task anyway, you shouldn't be able to, you should be able to win with probability essentially the time you spent over the total hash rate in the system. That's exactly like in Bitcoin, right? And in particular, no matter what X you chose, you shouldn't be able to, if you're trying to cheat the system, game the system by running in less than Tn time, right? I have no idea where your useful input came from. It's external to the system, but no matter what you do, if you try to spend less than Tn time and kind of cheat, you should not be able to open a block or to win the lottery with probability. So basically, these two things say that the same uniform hardness guarantee of Bitcoin, right? If you expend T of n time, or GPU cycles or whatever, you should be winning, opening a block with probability the runtime you spend divided by the total compute in the system. Make sense? Yep. So okay, so not quite. So morally, what we'll do is, and this is very high level, and I'll describe the protocol in a second. But morally, what we will do is the observation is philosophically simple, right? So what we'll do is, instead of hashing in Bitcoin, what we did is we just asked for a completing string, hashed it, and saw if it's smaller than some threshold, right? Here we will not hash. Instead of just trying an arbitrary string, we will hash the output of some perturbation of the actual useful task, and we will use that as the string, the input string that we. So instead of just trying to guess random strings that will make the hash function evaluate to something small, you'll just output the. You will just input the output of your useful task on a perturbed input. Why is that? Because if x is perturbed, you might hope that f of x, this x tilde, also has enough entropy in it, and then you can use this like leftover hash lemma to argue that you can still, there's enough entropy for this to be uniformly, there's enough entropy to extract here for this to be a random guess. Okay, I'll explain exactly how this works. This is the intuition. Okay, the most important parameter here is actually this parameter, which is called the overhead, right? So the whole point here is trying to piggyback on the useful compute that you're going to do anyway, right? So I claim that even if you have a factor 2 here. This is kind of trivial. Why is that? By clearly with a multiplicative factor of 2, if solve runs in twice times T of n, this is essentially trivial for any task. This is trivially achieved. Why? Well, I'll just let the miner compute the useful work separately, and I'll just draw a random input from the hard distribution for T, the worst case distribution, and I'll let them solve those 2 problems separately. That will take at most twice times Tn, but it loses all the purpose, right? The whole point here is merging, like it's 2 for 2, not 2 for 1, right? The whole point here is getting 2 for 1, like doing mining and useful computation all at once. So does that make sense? So all we're fighting for here is a factor the whole point here is making the overhead little o of 1 as opposed to constant, right? And in practice, this is what matters. Yeah.
I don't think I was tracking protocol you just gave for cap equals 2. So
yeah.
If that's the solve functionality,
yeah,
with overhead factor 2, what's the corresponding verify functionality?
You'll just verify. So y would be, so your output y, so y would be f of x, right? Just the worst case algorithm for x. And pi will be just a random, just the usual useless, just a random. I would say, okay, I'm thinking of the specific task we're going to consider, which is matrix multiplication. But you can think of this for matrix multiplication, just multiply 2 random matrices, right? So that's going to be.
Pi then consists of
the,
2 random matrices and their products.
Just the product, just the answer, which is a random string, right? So that's kind of that's essentially. So let me say it this way: one way to get to implement Bitcoin is just re-implementing Bitcoin based on random matrix multiplication. That's trivial, right? If you just, in fact, there is a chain that's doing that, right? So why? Because that's just one way to ensure random inner product is just one way to implement universal hash functions, right? So that's trivial. The problem here is that here you have a specific, it's not 2 random matrices, 2 arbitrary matrices that of your choice that you're going to choose. Okay, so maybe it will be clear when I so is the challenge clear here? I don't know if it was. So the goal here is that no matter what x, the key difference here is that the miner picks x, right, which is the useful input. I have no idea where it came from. It could be like 2 matrices that I multiplied at home a week ago, right? And you'll never know so I could just reuse this computation. I can multiply the all zeros matrices, diagonal matrices. So the goal here is to ensure that no matter what x we pick, the dishonest miner picked, the probability of verify accepting this this proof is not going to be larger than the honest miner who's going to actually invest those T resources, right? Otherwise, this completely disincentivizes the honest miner to participate. All right, so I think it will be easier to see when they describe the actual protocol. All right, so as I said, the task we consider here is matrix multiplication, and for obvious reasons, right? So matmulls are not just the backbone of training and inference in AI. It's the backbone of general compute, right? Quantum simulations, graph search, compression search, scientific computing, image processing. Everything is basically running on GPUs today and using matmulls. So matrix multiplication is essentially, we view it as a proxy for general compute. And so our baseline is going to be naive matrix multiplication simply because we're aiming for a practical, useful proof of work protocol. However, we are our security guarantee is going to allow the dishonest miner to use even fast matrix multiplication. So it's going to be secure under a certain conjecture against any type of, unrestricted dishonest miners. All right, so here's the task, right? So remember what the task is. The miner is uploading, or not uploading, it's the wrong word, is choosing her favorite two matrices. In the honest case, these might be the weight and activation matrix from some, DeepSeek model or, some quantum simulator or whatever. And she's going to multiply them anyway, right, for her application, right? So why not? So the goal here is to compile this protocol with a slight overhead, little of one overhead, to do 2 for 1. So to compute the output and to produce this lottery ticket, which has the same Poisson behavior as Bitcoin. Okay. So the first natural idea is, this is essentially a random the first idea is to use the classical random self-reducibility of matrix multiplication, right? So, and again, it's instructive to think of A and B as the all zeros matrix, because that certainly is not a hard problem, right? The dishonest miner will choose the all zeros matrix, right? Because, so if we don't touch the matrices, that's obviously broken, right? Like it's going to cost 0 time to multiply, right? So instead, what we're going to do is, the natural idea is to just sample two random matrices, let's say ±1 matrices, and to just do the proof of work, ask the miner to multiply, A plus noise, B plus noise, right? So even if A and B are the all zeros matrix, this is going to be a hard problem, right? And again, the way you draw the random matrices using Fiat-Shamir, I'm not going to get into this. Just there's no interaction here. The miner just takes the hash of the previous block as a seed and generates the noise, samples the noise matrices to himself, and that's secure. And now the output is going to be, basically just the output of C. Okay, and so that's going to be the output. All right. So let's think of it. So obviously, this step is going to require n cubed time, right, using naive matrix multiplication. And it's pretty easy to see that if C is the product, if E and F are random matrices, then the output transcript C is essentially a random string, right? Right, because that's one way to implement pairwise independent hash functions, at least if we're over like F2 or whatever. But then, okay, so great. So this required n cubed time, and it has the same chance of opening the block for no matter what A and B were, right? What's the problem? The honest miner, now for my deep learning application, I'm not interested in A prime times B prime. I need A times B, right? So I need to peel out the noise, right? So unfortunately, peeling off the noise requires me to open the brackets here and compute 2 other products. So what's the overhead here? Say it's at least 2 times. So it's completely useless, right? I might as well just give the miner 2 separate matrices, like another separate random matrix to multiply, and just test that. And that completely defeats the purpose. All right, so what's the idea to mitigate this? Maybe we can use structured noise, okay, which is easy to peel off. So we won't pay the 2 n cubed extra terms. Does that make sense? And the problem here is that, for example, what we'll see in a second is if we choose low rank, if we choose E and F to be low rank matrices, then peeling will be great. Well, right, because it will no longer require, if E and F are low rank matrices, all of this thing requires little o of n cubed time, right? But what's the problem here? Suppose E and F are just random. Yeah, okay, so just a second. So again, suppose E and F are just random low rank matrices, okay, rank R matrices. So now we fix the peeling problem. Peeling is easy because you just need to subtract low rank matrix multipliers, which is little o n cubed. What's the problem here? If we choose A and B, exactly. If we choose A and B to be the all zeros matrix, what are we left with? We're just left with multiplying two low rank matrices, which breaks security. The honest miner will spend n cubed, where the dishonest submitting the all zeros will spend little of n cubed. This is completely broken. So it looks like, we're trying to pull the rope from both ends. And it seems that, for a while we thought, okay, this is impossible. And the key insight is really to use, the key observation is the following, that for the useful miner, for our application, we don't care about, all we care about is the output of the matrix, right? The product of the matrix, right? We don't care about anything else except the output. But for the proof of work, no one said that we had to do it on the output. Maybe we can do it on a space of intermediate computations. And that really breaks the symmetry between, breaking the symmetry between the output and the intermediate computations is really the key idea here. So, and actually, so the idea is to give a trapdoor that makes peeling the noise easy. But this trapdoor is completely useless for intermediate computations. Like locally, you cannot exploit this structure of the noise. So the goal is to have some low entropy structured noise, which is globally very useful because you can peel with it, but locally it seems completely indistinguishable. And that's where and the idea is to just piggyback on the way GPUs actually multiply matrices, which is a tiled way, right? They just load R by R tiles and multiply those blocks, R by R blocks. So here's the full scheme, which is very simple, right, and practical. So the miner, whether honest or dishonest, submits A and B. And now we're going to add random low rank matrices. How are we generating them? Or just random matrices, which are, in their low rank decomposition. But now the key insight is instead of doing the proof of work on the output, just hashing the output and seeing if it evaluates to 47 trailing zeros, we're going to do this. We're going to do this on the space of, so peeling is great, right? It's going to take little of R n squared time. But now, okay, so let's take Swastik's extreme example. Suppose the dishonest miner submitted the all zeros matrix, which is the easiest matrix he could try to cheat with, right? But now I'm going to basically, my goal here is to tie the hands of the, I want to force the algorithm to not be able to exploit the low rankness of the matrix. And the way to do this is to force the miner to compute all the intermediate inner products between, all the intermediate tile multiplications, which is what the worst case algorithm would do, right? It would not, so I'm basically forcing the dishonest miner to unzip the low rank matrices and compute all the intermediate tiles, right? So I'm gonna, for every pair of tiles, I'm gonna just take those two tiles. I'm going to hash them, and I'm going to check every R by R tile product is going to give you an independent lottery ticket to a chance of winning, right? So now there are actually n cubed over R cubed such tiles. And if the dishonest miner will not compute them, he won't, is it clear that this completely kills the low rank algorithm? Because now I cannot exploit the low rankness of the matrices if I want to win all those lottery tickets. Now, if the matrices are rank R random matrices, then marginally, that's the least we can add. Marginally, it's a R-wise independent distribution. So marginally, all those tiles are completely random, right? So at least marginally, multiplying those, winning this thing requires R cubed time, right? Using naive matrix multiplication. Does that make sense?
But now the verifier also has to, and when you ask to check the show the whole transcript.
No, so that's the point. So only when you win a block, you need to prove, so the miner commits to the matrices, A and B, whatever they are. And only when you open a block, which happens once in a decade, only then you need to actually prove that. So the amortized time is very cheap. You see, so you only need to send the actual thing only when you open the block. So all you need to do is an extra hashing operation which in practice is like 10, 15% overhead on GPUs. So it's very cheap actually. Yeah.
I just want to make sure I understand the idea
Yeah.
is that you have a baseline problem, which is given two low-rank noise matrices drawn from some distribution.
Yeah.
Plus, you have to prove in a specific way what you're doing. That like baseline problem takes order n.
Yeah.
And then you're saying that additional property you would like is that no matter what matrices you choose to find in little lower than cube time, there's no way that's going to let you solve the joint problem faster than order n.
Exactly.
You may as well take whatever matrices you already wanted to multiply and
Exactly.
sort them in. It's not going to cost you, it's going to cost you a little overhead. And no matter how you choose them, it's not going to make you a better model.
Exactly. Exactly. That's the idea. And we'll see in a second that there's nothing holy about low rank noise structure. That, you know, that's just one scheme. But right, so we all agree that marginally every R by R tile is random, and random distributions are the hard distribution from matmul. So that requires presumably R cubed time. Alas, all of those lottery tickets are very correlated because there's very little entropy in the system, right? So the hardness conjecture here, which we thought about, including Mark, I think, and Orr, and Noam Nissan, and Rafael Paz, many clever mathematicians thought about, and I assume that if Mark didn't break it in half a year, then it's solid. But it's but the subtle, so it's basically a direct product of correlated instances conjecture, right? So remember, marginally, you require R cubed, but the conjecture is that to compute all the lottery tickets, you actually need n cubed time, which means that there's no way to correlate those answers. And actually, there are some stuff you can try to do, right? Because there's very little entropy here, then you can see that computing any strip of R by n matrices all the rest will be random linear combinations of those tile multiplications, but that entails solving a linear equation, which is not cheaper than the original thing. And actually, it's pretty subtle. This conjecture is actually not quite true. So using fast matrix multiplication, or the fast rectangular matrix multiplication, you can actually compute those two matrices using rectangular matrix multiplication in time roughly much faster than something like n squared as opposed to n squared times r. And then you need only n over r squared times to run this procedure to compute all those intermediate tiles. So you can actually beat n cubed with fast matrix multiplication. So our real conjecture in the paper is this, and that we believe that's the best attack we found. Of course, it's still a theoretical attack, but even theoretically, we couldn't find, it's been almost a year, a better attack than this one. I just want to end by one more. Do I have five more minutes or two? Okay, I just want to say there's nothing holy about low rank. So here's a self-canceling noise scheme, which I think is even more elegant. Instead of drawing two low rank matrices, how about we just multiply A and B by random rotation matrices? Okay. And then we let this matrix be A prime and B prime. Then we just ask to do the same tiled protocol on the product of A prime and B prime. Okay, and let's assume A and B are full rank. Otherwise, if they're the all zeros matrix, it doesn't make sense. This will be still zero. But if they're full rank, then the nice thing we get here is that the noise completely cancels. So A times B prime is equal to A times B. So there's no need for any peeling whatsoever. Of course, the overhead here is big. If R is just a random rotation matrix, it's going to take you R cubed time to just rotate. But we can choose those matrices to be just pseudo-random rotations, like the randomized Hadamard matrix. Okay, so that's going to be very cheap. It's going to take like n squared log n time, which is little of n cubed, to rotate the matrices to compute A prime and B prime. And now the same thing happens. So the noise has very nice global structure. You can multiply with Hadamard matrices very fast using FFT, right? But locally, there are no cancellations, right? Locally, to compute arbitrary sub matrices of the Hadamard matrix, that's not known to be easy. In fact, there's a very nice work of Kidlai and Umans that shows that it's essentially like a local polynomial evaluation problem. So again, this is a conjecture, but that just shows you that there's tons of things you can try to do. You don't even need to peel the noise, right? That resembles like secret sharing, right? Like each of us gets those tiles, they're completely random, but if we add everything together, we get exactly the secret, which is the product result, right? So actually, I think this scheme could potentially be more efficient. We're trying to implement this as well. That's it. I think the main like story here is that Bitcoin showed that the like philosophical breakthroughs that you can turn a very specific kind of artificial computation into a currency, right? Forget the mathematics. I'm just talking about the societal implications. What useful proof of work is showing with matmols being proxy for general compute is that you can turn general compute, any compute in the world that's happening, let's say 90% of this, into a currency, which I think is much more like, it seems like a much bigger idea. It's not just this toy example of Bitcoin. Forget the energy saving problem. And it raises a lot of other interesting questions and mechanism design of how to enforce honest behavior, what's the equilibrium, how does the entropy of this system evolve where there are external, right now there's dual income. There's the income of the honest miner from the AI work, and there's the income from the block reward. So what's the best strategies? What's the equilibrium here? What's the entropy? How does it evolve? And how general is our scheme, right? What did we use about matrix multiplication? Essentially, we use linearity, right? And this random self-reducibility, but that conceivably pertains to other problems. So I think you have to be composable, right? Like shortest paths probably won't have this compiler that can compile into a short, but it's probably much more general than this thing. And I think I'll stop here. Yeah.